Hello everyone, today we're talking about orthogonal sets, material from 6.2. So let's jump in with a definition. Let's say we have a set of vectors, say u1 through up. Just say these are an Rn. We say that this set is orthogonal if, well, let's see. So this is a collection of vectors. We want to know what it means to be orthogonal. We know what it means to have two vectors, a pair of vectors being orthogonal. So what we want is that when I take any two vectors from this collection, they should have a dot product of 0. They should be orthogonal. And this should happen for all I not equal to j. Okay? So just as a concrete example, if I'm in R3, I can look at this set here. And right, there's three vectors here. So if I try to verify that this is an orthogonal set, I have to look at each pairwise dot product. There's three computations to make here. Three dot products to check. So for instance, 3, 1, 1 dot minus 1, 2, 1 is, let's see, minus 3 plus 2 plus 1. That's 0, right? And you can check that the first and the third and the second and the third are also have a dot product of 0. A collection of vectors is what's called orthonormal if the collection is orthogonal. I'll say if it's orthogonal and each vector is a unit vector. So the length is 1. And just as an example of that, in R2, I've got this guy here, minus 1 over root 5, 2 root 5, comma, 2 root 5, and 1 over root 5. So that's two vectors in R2, and if you look at the dot product, it's clearly 0. And if you look at the length, let's say this is like u1, the length of u1 is, right, the square root of, well, minus 1 over root 5 squared plus 2 over root 5 squared. What is that? That's going to be the square root of 1/5 plus 4/5, which is 1. Okay? So each vector, and this also, if this is u2, this also has a unit length, and so this is an orthonormal collection. And so let me go to the next page, the kind of one important feature of these orthogonal sets. So, we've been talking about sets of vectors and several pleasing properties they might have, and one of the most important is the notion of a linearly independent set. And so here's our kind of first theorem here, is that if S u1 through up is an orthogonal set of non-zero vectors, that's important, in Rn, then S is a linearly independent set. Okay? And maybe just say, well, okay, so let's prove this. Well, remember now, what does it mean to be linearly independent? The only way to write the 0 vector should be as a linear combination of these vectors is as the trivial way. So suppose we could write the 0 vector as a linear combination of these given vectors. What we want to show is that all of these C1, C2, the coefficients, the weights, have to be 0, right? Well, what we can do is apply, dot to both sides of this equation. What you get is, well, 0, which is 0 dot u1, is equal to this whole thing dot u1, so the thing from above, let me write it. And properties of dot product that we saw last time says that you can distribute dot product. So, I mean, if you like, this is, remember, dot product is a kind of matrix multiplication. So we know that matrix multiplications has a distributed property. It also has this nice property that we can pull out constants, these coefficients. So this is going to be C1 times U1 dot U1 plus, well, what happens here? This is going to be C2 U1 U2 dot U1 plus dot 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 plus CP UP dot U1. And what do I get here, right? So we're assuming that this is an orthogonal set. So what do I know about U2 dot U1? That's 0 because I've assumed that every dot product of different vectors is 0. The next one's 0, the next one's 0. This UP dot U1 is also 0. So this actually goes away. And what I have is that 0 has to be equal to C1 times U1 dot U1. But what is U1 dot U1? That's the length of U1 squared. And we know that we're assuming this is a non-zero vector, and the length of a non-zero vector is always non-zero. That's something that will actually show up on your homework. So this guy is not 0, and I'm multiplying it by something to get 0, so that implies that C1 equals 0. And what you can do, so we've now showed that C1 has to be 0, and you can do this same trick with, applying the dot with U2, the dot with U3, etc., up to UP. And similarly, what you get is that all Ci equals 0, which implies that the set is linearly independent, because the only way to write the 0 vector was the trivial way. Once we write the 0 vector as a linear combination of the U1 through UPs, we know that it's got to have all those weights to be 0, which means it's a linearly independent set. The only way to write 0 is in the trivial way. Okay. So definition now. So we should now realize that, let's recall that why did we like linearly independent sets? Well, remember, that was one of the properties of a basis. So you want to think of orthogonal sets as somehow even more special than linearly independent sets, right? Linearly independent sets were nice because there was no redundancies in the collection. There was no non-trivial ways to write one vector as a linear combination of the other. And orthogonal sets are kind of even more special. And the definition I want to write down is an orthogonal basis, the notion of an orthogonal basis for a subspace W is a basis consisting of an orthogonal set. Well, let's say it this way. It's a basis that is also orthogonal. So it spans and is orthogonal. Okay, so this is a special kind of basis for a subspace. Maybe just go back to this example here. We saw here that this was a collection of 3 vectors that was orthogonal. Therefore, this collection is a orthogonal basis for R3. Okay. This one down here is actually an orthonormal basis for R2. Okay, so why do we care about orthogonal bases, right? So I'm saying they're somehow special, but here's the fact, the theorem. Suppose, say, U1 through UP is an orthogonal basis for a subspace W, and let's let Y be a vector in W, then, well, we know that we can write Y, since this is a basis, right? You guys know that since this is a basis for W, any vector Y can be written in a unique way as a linear combination of the basis vectors, right? We know that there's one and only one way to write Y as a linear combination of those basis vectors. And the idea is that if it's orthogonal, then there's actually a really nice formula for what that weight is. Then it turns out that Cj, the number Cj that goes on the jth vector, is just given by Y dot uj divided by uj dot uj. Okay, so this is a number because this is a number divided by another number, and the proof of this is just exactly what we just talked about. That if I take y dot uj, if I take this vector y dot uj, then what do I get? Well, this is c1u1 plus dot 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 cpup. Right, that's what y is, dot uj. And similar argument now, when I take this collection of vectors, this linear combination, and dot it with uj, it's going to go to 0, right? So every time I see a vector that's not uj, it's going to go to 0. What's going to be left with is just cj of uj dot uj. All the other terms, when I distribute this guy, will go to 0. And then you solve for cj, right? So just divide by the uj dot uj thing, and you get what you want. Okay? So that's the proof of that formula. And again, this is really nice because it tells you that when you have this orthogonal basis, you give me a vector y, and I can just very quickly tell you what those weights should be that give you a representation for y. Okay? So, quick example. If this is a vector y and orthogonal basis that we looked at above, let me remind myself what that was. So this is the orthogonal basis that we talked about above, the orthogonal basis for R3. So I should say this is the orthogonal basis for R3. Okay. Then I want to write y as, c1 times, let's say this was u1, u2, u3. I want to write it this way. And in general, this would involve, solving a linear system, doing some row reduction. But, what this is showing us is that you don't have to do all that. You just make a calculation. Then, for example, let's say, I don't know, C2 is going to be, if I want to know what that C2 coefficient is, I take the vector y, dot it times u2, divided by u2 dot u2, and let's go through that calculation quickly. So what's y dot u2? So y dot u2 would be 6 minus 6, because I've got a minus 1 here, plus 2 minus 8, divided by u2 dot u2. So what is that? Minus 1 squared, which is 1, plus 2 squared, which is 4, plus 1. So what I get here is, looks like, so the minus 12 divided by 6, it's a minus 2. Okay, and so that number here would be minus 2, and I'll spare you the other calculations, but in a similar way you can get C1 and C3, and that'll tell you, in fact, I wrote this down just in case you're wondering, in fact, y is u1 minus 2u2 minus 2u3. Okay, so that's the idea here. Again, once we have an orthogonal basis, we can represent every vector. Well, we know we can represent every vector as a linear combination in a unique way, but those coefficients that give you the weights of that linear combination come from a nice formula like this. Okay, so we'll see applications of that next time. See you then.